Then let's talk about from sphere. Let's go back to more practical case. Reality. We're talking about most cases, not exact spherical, so-called non-spherical particles. Okay. Similar to spheres, people find the random packing of bimodal. Even if they are non-sphere, they also lead to increased packing. So in this case, okay, we are no longer dealing with sphere. Even this, if they are non-sphere, if we have bimodal, we quite often also get increased packing density. Okay, and the packing density depends on, in this case, reality, still depending on the size ratio between the two. If we are talking about bimodal, the two different mode of particles. Depend on the volume or weight fraction of larger or coarser versus smaller or finer particles. And since it's no longer a sphere, the shape effect comes into play. Make sense? We are talking about non-spherical, so the shape would come into play. Whether we are talking about cylinders, plates, or cubes, they all pack somewhat differently. Okay? So here I'm talking about fiber. Random packing density versus aspect ratio for fiber. Fiber essentially from geometrical point of view is just a long cylinder, right? Ideal fiber is just a long cylinder. So you see, okay, random packing density, if my size ratio, I should not be 0, it should be close to 1. Start from here, 70 some drop all the way to almost 0. If your fiber is extremely long, extremely narrow in diameter, if we're talking about random, yes, of course, if we are talking about random, if they have such large aspect ratio, the packing density is terrible, extremely low. Fiber, okay? Then, this is what we said. That's why for typical whiskers, you do not want your whiskers to be too long if you are incorporating them into your system. You do not want your fiber, if you're talking about whiskers, do not want them too long. It's difficult to process unless you purposefully using machine to really align them, which is difficult, not simple. Okay. And then here we are showing a table for whiskers to particles. We are showing a viscous to sphere particle mixture. Particle diameter versus viscous diameter ratio. But then for the viscous, we have different aspect ratio, right? We have different aspect ratio. Let's see between these two. Between these two, we have the same types of whisker, but we are adding different volume percentage of the whiskers, right? We have different volume percentage of whiskers, and then particle diameter versus whisker diameter ratio. Particle diameter versus whisker diameter ratio. Particle diameter, if it's 0, which means particle diameter is extremely what? Particle diameter to whisker diameter ratio is 0, very small. The particles are extremely small, which is, okay, the extreme case, the particle will always find its way around the whisker and fill it up. And as a result, we have what? Reasonably high packing density. Make sense? But as we increase the volume fraction of whiskers, my packing density become lower. Make sense? On the other hand, let's go to the other side. Now my particle compared with whiskers are larger in diameter. My particle diameter is much larger than whisker diameter, which means whisker is relatively thin compared with my particle. Then horizontal, if we just follow this line, we find if we keep the same whisker going along this horizontal line, I keep this whisker aspect ratio, but gradually I'm making my particles relatively what? Larger and larger, and I'm getting lower. Okay, getting lower for finite range. But then when it goes to infinity, it's a different story. When it goes to infinity, it's a different story, because essentially you have no whiskers, just all particle, right? Now you go back to like packing of particles again. Make sense? Then it goes up again. So kind of like for this one, but this is extreme case. Then between this line and that line, no matter what is the particle to whisker ratio, as I increase whisker content, my packing density suffers for random packing. Okay? So question. Okay, so the essence is that be careful with when you increase the volume fraction of your so-called viscous or fiber. At the same time, be careful from here, let's say 50 to 50, compare 25 to 25. Be careful with increasing your so-called aspect ratio. You see that? From 25 to this 25. You see what I mean? From 25 to 25, 65. Let's go down here. From here, these two columns. I'm both having 25 volume percent of viscous, but then one gives me 75, the other only gives me 54. What's the difference between this guy and this guy? It's the aspect ratio for my fiber. Okay, so there's a lot of information just in these tables, but the essence is that, as we mentioned, be careful with when you increase in your so-called relative volume fraction for your viscous. Be careful when you change your viscous aspect ratio. Be careful when you change the relative size of your particles versus the viscous diameter. All these parameters. Okay, you said, boy, that's complicated. Well, it is complicated, but I believe there are probably geometrical model that people can model these easily. Okay.